Number 75. For the following exercises, use the vertex of the graph of the quadratic function and the direction the graph opens to find the domain and range of the function. Okay, so these are parabolas, as you know, and the domain will always be negative infinity to infinity, the open interval from negative infinity to infinity. It's the range that'll vary depending on the parabola. So if the parabola opens upward, the vertex is the lower end of the range. If the parabola opens downward, the vertex gives you the upper end of the range. Okay, so for 75 we have vertex, call it V1, -2, and it opens up. I'll just write up. Alright, so again the domain, D let's call that, is negative infinity to infinity. It doesn't matter what parabola you're talking about, as long as it's one of these quadratic functions, that's going to be the domain, opening up or down. And then the range, call it R. Well, since it opens up, the vertex is at the bottom end of the bottom part of the parabola. So the y value -2 is the minimum value of that parabola. So it starts at -2, the range that is, -2, and it keeps going up, up, up to infinity. And that's it. Number 77. Vertex is -5, 11. And opens down. So I'll write down. Okay. So that means the vertex is, since it opens down, the vertex would be the highest point on the parabola, and the y value there would be the maximum value of that parabola. So that'll give us the range. The domain again is negative infinity to infinity. The range is negative infinity to 11. Number 79. For the following exercises, write the equation of the quadratic function that contains the given point and has the same shape as the given function. Alright, so by shape they mean if the parabola has been stretched or compressed, as in the section we studied on transformation of functions. You know, it's going to have that same stretching or compressed appearance. Alright, so this one has the point 1, 1. And has a shape. So I'll say shaped like, it's not exactly scientific terminology here, but that's okay. You understand what I mean? It's shaped like f of x equals 2x squared. Alright? So this 2 will, if you take y equals x squared, you put that 2 in front, that's going to cause a vertical stretch by a factor of 2. If you had y equals 2x squared, divide both sides by 2, you'll have y over 2 equals x squared. The 2 under the y causes a vertical stretch, if you remember from the section on transformation of functions. Alright, so yeah, that section was important because you'll see it again. It keeps haunting you, right? It'll come back again also when we cover trigonometric functions. Alright, it'll come in very handy in that section too. So if you don't know it, If this is confusing you, what I just said, I highly recommend that you go back to that section and hit it again until you get it, all right? Because this stuff does come back. These techniques of transformations apply to all kinds of different functions. So the vertex, it says, is on the y-axis. So let's say the vertex, since it's on the y-axis, that means the vertex has x-coordinate of 0, and whatever the y value is, call it k. All right, 0k, that's the vertex. So what I'm doing is I'm writing down what I know, and it will satisfy this. It will satisfy f of x, standard form that is, f of x equals 2 x minus h quantity squared plus k, where hk is the vertex. Okay, so I'm just using that. That's the a in the standard form, the a constant, right? And writing it out in standard form. Hk is the vertex. Well, we already know what h has to be. It's 0. But I'm just stating this in general right now. We'll plug that in later, okay? So hk equals 0k, right? What's k? Well, I don't know. We'll find out. Write down what you know. You know, don't try to write down things you don't know yet, because you don't know. We'll find out. So write down what you know, so you'll know what you know. All right, and the function has the point 1, 1. Okay, so let y equal f of x. Let's start off with that. Let y equal f of x. And then we have y equals, using the standard form, 2x minus h squared plus k. Alright, and now we plug in. Remember that this is kind of like what we did before in some of the problems. Plug in what you have. Right? You've got x is 1, y is 1, so you let y equal 1. We know that point is on this graph, 1, 1. And then we've got 2. X again, let that equal 1. We know that h is 0, so plug that in. The only thing we don't have here is k. Looks like we're going to find out what k is, because that's the only unknown we have in this equation. All right, everything else is known. So we've got 1 minus 0 squared is 1. So that's just 2. 1 equals 2 plus k. Subtract 2 from both sides, you get k equals, I'll write therefore, k equals negative 1. Okay, so that means we have f of x, going back to the standard form, 2x minus 0, again h is 0, squared, and then k is negative 1. And so this is equal to 2x squared. That simplifies to 2x squared minus 1. And that's it. Number 81. So it contains 2, 3. and it has a shape of f of x equals 3x squared. Okay, so the vertex is on the y-axis. Again, that means the x-coordinate has to be 0 at the vertex. So the vertex is 0, and then whatever k happens to be. Alright, so it's going to satisfy, will satisfy the this standard form, f of x equals the 3 and then x minus h quantity squared plus k. Alright, and of course again hk is the vertex. Alright, I won't bother writing that down like I did in my last problem. So hk is 0k, alright, I won't bother writing that down either like I did before. And the function contains that point. So let y equal f of x. Alright, so we have y equals 3 quantity x minus h squared plus k. And so you let y equal 3 because this is a point on the graph, so y is 3 and that equals 3, and then let x equal 2 and h is 0, so 2 minus 0 squared, and then we'll solve for k in a second. And so this is 4, 2 minus 0 squared is 4, times 3 is 12, so 12 plus k, and then subtract 12 from both sides. So k is equal to negative 9. Okay. Therefore, f of x is equal to 3 times the quantity x minus 0 squared, and then we just found out k equals negative 9, so add that in there. And so simplifying, we get 3x squared minus 9. So there's our function. Number 83 contains 4, 3. And it's shaped like f of x equals 5x squared. Okay, so the vertex is on the y-axis. Once again, that means the x-coordinate on the vertex has to be 0 in that case. So the coordinates that we know so far for the vertex are 0k. And it's going to satisfy, will satisfy, f of x equals, using the standard form and getting the 5 from this, since it's the same shape. Again, the 5 will cause a vertical stretch of y equals x squared. Alright, so you got to put that in there, and you've got x minus h squared plus k. Alright, hk is the vertex. So hk equals 0k, as we know, and the function has the point 4, 3, as we know. So we let y equal f of x. And so what we have then is y equals, get the 5 from there, 5 x minus h quantity squared plus k. And so let y equal 3 and x equal 4, since that point is on this graph. So we've got 3 equals 5, and then 4, h is 0, squared, and then k is unknown, but we'll soon find it out. And so 4 squared, 4 minus 0 squared, that's 4 squared is 16. 5 times 16 is 80, so we've got 80 plus k. Subtract 80 from both sides, we get k is equal to negative 77. Alright, so therefore f of x is equal to 5, quantity x minus 0 squared, and then k was negative 77. So simplifying, we get 5x squared minus 77. There it is. Number 85. Find the dimensions of the rectangular corral producing the greatest enclosed area given 200 feet of fencing. Okay, so whenever you're dealing with a word problem, it always helps to draw a picture if that's appropriate, and it usually is. Alright, it helps organize your thoughts, and you don't want to, especially in a test situation, don't try to do it all in your head. You may make mistakes, you may forget, unless you're super genius brilliant. Alright, most of us have to use pictures. It really helps, actually. Alright, well, it says we've got 200 feet of fencing. That means all the way around adds up to 200. So we've got 2 of these L's and 2 of these W's, right? If this is length and call that width, you can call these whatever you want. Call that width, call that length if you want. It really doesn't make any difference in the problem. So it's up to you. Anyway, you've got 2 of these L's plus 2 of these W's add up to the total fencing, right? So 200. So you write that down as an equation. 2L plus 2W is equal to 200. Alright. So, divide both sides by 2. Simplify this. L plus W is equal to 100. Alright? And then solve for one of these variables. You don't want 2 variables to work with, but it's easier if you solve for one of these variables in terms of the other. So it's your choice. You can have W equals 100 minus L, or L equals 100 minus W. That's what I chose. It's really immaterial which one you choose to solve for. Alright, so L equals, L is now written in terms of W. L is written in terms of W. It's 100 minus W. Okay, now what are we trying to do here? That's the question. We want to find the greatest area with this much fencing, the greatest enclosed area, or find the dimensions rather, that'll give us the greatest enclosed area. So what is area on this? Well, area is length times width, LW. Right? Length times width. Well, we're going to use this to figure out the problem. Okay, so use the area. And what is L? L is 100 minus W. We already figured that out. So write that in there, 100 minus W instead of L. Times W. There's your length times width. Alright? And then multiply it out. Distribute that, rather. Negative W, I'm going to write the negative W squared first, plus 100W. Now you got a quadratic equation. That's interesting because that's what we're working on in this section, right? So you know you're on the right track. Well, what am I trying to do with this quadratic? Well, quadratics have a vertex, right? That would be either the minimum or the maximum value for the parabola at the vertex. And this vertex or this parabola represents area, right? Area. So this rather the parabola opens downward because That's leading coefficient is -1. So it's a negative, so it opens downward, which means the vertex will give you the maximum area, the y value at the vertex. So what we need to do is find the y value of the vertex for this function. Okay? So you can do it either -b/2a, call this function a of -b/2a, capital A that is. Or you can do my favorite, completing the square. Alright? So that's what I'm going to do. So what I'm going to do is, this can be written as, factor out that -1, w squared minus 100w. Alright? So I'm just taking a common factor of -1 out of these two terms. Right? If you distribute that back through, you'll get this again. And then I'm going to complete the square on what's in the parentheses. So you take half the coefficient of x. In this case we're using w's instead of x's. Okay, so half the coefficient of w. Let me do it over here. Call this our scratch area. So I'm going to take half the coefficient of w. That's half of -100. And square that. And then we're going to add and subtract that in parentheses. So this is equal to -50 squared. And that equals 2500. So that's what we're going to add and subtract in parentheses. So we've got negative w squared minus 100 w, add and subtract, plus 2500 minus 2500 inside the parentheses. Alright, so now you're going to remove this term. First you multiply it by -1 before you bring it outside of the parentheses. So that's going to become plus 2500. So you've got w squared minus 100 w plus 2500 and then plus 2500. Okay, so this is a perfect square trinomial as always. So we got negative, and that's going to be w minus 50. You can take either half of the 100 or square root of 2500 to get that 50. Either way works. Squared plus 2500. Now we have a quadratic in standard form, and we can read the vertex right off of there. So let me go up here, follow the arrow. So the vertex V is 50, 2500. Now we're not working with x and y's, but the x here is w actually, alright, width. So that means if you have a width of 50, you'll get a maximum area of 2500, alright. So w equals 50, that's going to give you the maximum area. Well, what's the length if w equals 50? Go back here, L equals 100 minus w, so that's 100 minus 50. So basically you get a square Corral. And you know, if that's the case, you might wonder why you don't see square Corrals too much. I don't know, maybe it's the way things work out in terms of land, or maybe the land isn't conducive to giving you a square Corral. Maybe parts of the land might not be good for a corral, you know. So if you have a square shape, it might jut into parts of bad land, so to speak. You know, there's lots of reasons why people won't build a square corral, even though that'll give them maximum area. You'll see a similar problem probably in calculus. When you take calculus, they've computed the dimensions of a can that'll give you the maximum volume, like for a soda can or a beer can, and it's almost like a squarish kind of a shape to the can. It's not very long, it's short and squat, and it's kind of a square shape, and that uses the minimum amount of metal to make the can, so it would be the cheapest can to produce. But customer market research has found that people do not prefer that shape of a can, so they've abandoned that, and so they're making the cans more expensive than really they need to, because people don't like that shape. So, you know, there's lots of reasons why they won't follow the mathematics. I mean, that's what the math tells you. A square corral in this case will give you the maximum area. But there are other things to consider in the real world, right? So there you go. There's your answer. Use it if you want. Okay, number 87. Find the dimensions of the rectangular corral producing the greatest enclosed area split into 3 pens of the same size given 500 feet of fencing. So it's a lot like the previous problem, except they've thrown us a little curveball here, so to speak. So it's a rectangular corral again, split into pens, 3 pens of equal size. So here's our picture. I'll try to make these pens as equal as I can. Alright, and so you got 1, 2, 3 pens of equal size. And let's say this is the length L, and this is W. Okay. Alright, so all of this is made of the fencing that we're given, which is 500 feet. So how many W's are there? We've got this section, this section, this section, this section, and then length we can call all of this and all of that. So we've got 2 of the L's and we've got 4 of the W's. Okay, so 4W plus 2L is equal to 500 feet, right? 500 feet of fencing total. So you can simplify this a little bit. I mean, why not if you can, right? You don't have to, but it'll make things easier. Divide both sides by 2. You can see 2 goes into both sides evenly, so you've got 2W plus L is equal to 250. Okay, so now solve for one of the variables. In this case, it's easier to solve for L. Write it in terms of W instead of the other way around, because you'd write 2W equals 250 minus L, and then you have to divide both sides by 2 to get W equals so and so, right? So on and so forth. So it's easier to isolate the L here. So you got L is 250 minus 2W. Okay, so we've written L in terms of W. So once again, we want to maximize area. So write area equals length times width. Alright. And what is length? It's 250 minus 2W. Times, there's your length, times width. There's your width. Okay. And so distribute that W through there and you get negative 2W squared plus 250W. So factor the negative 2 out. You get negative 2 times the quantity W squared minus 125W. Okay, and now I'm going to again use completing the square. Forgive me, but I like this method. And what you do is you take half the coefficient of the W and square it, and add and subtract it inside the parentheses. So you're going to, let me do it up here. half of negative 125 and square that. So that equals negative 62.5 squared, and that equals 3,906.25. Okay, so now you're going to add and subtract that inside the parentheses. So negative, in other words, you're adding 0. So you're not changing the value of this equation. So I'm still justified in using that equation symbol. Okay, so you've got plus 3906.25 minus 3906.25, like that. And then we bring this last term out of the parentheses, but first you have to multiply it by negative 2, and then you can move it out. So what you have left is w squared minus 125w plus 3906.25, and then out here negative 2 times negative 3906.25 is 7812.5 positive. Okay, and this is a perfect square trinomial, so that equals negative 2 w minus, you could either take half of that or square root of that, 62.5 plus 7812.5. So the parabola opens downward because of, we know that because of the negative leading coefficient. So the vertex gives you the maximum value. The vertex, let me write it over here, is 62.5 and 7812.5. The coordinates here represent width because of the w's, and a, think of that as being y. Usually you're working with x's and y's, right? Y equals blah blah blah. Usually that's an x and that's a y. Well, now you've got a w and an a instead. So this number gives you the maximum area. All right. So that means if the width is 62.5, what does that make the length? Length would be this, 250 minus 2w. 250 minus 2 times 62.5. That just happens to be 125. So the width is 62.5 feet and the length is 125 feet, and you get a maximum area of 7812 and a half. That would be in square feet, of course.